Last time we studied the following simple nonlinear elliptic PDE, where a lambda is a positive parameter and p is some exponent strictly bigger than 1. And we found out that there exists a value of the parameter called the extremal value, lambda star, such that if lambda is less than lambda star, then we do have a solution to this problem. And we even know that we have a minimal solution to this problem, that it's smooth, and that it's also strictly stable. When lambda is equal to the extremal parameter, then we only have a weak solution to that problem in the L1 sense. And for lambda larger than lambda star, there exists no solution. So now the question is to figure out whether this U star is truly a weak solution or if it's actually a classical solution. And this can be reduced to a so-called blow-up alternative. First case, U star is unbounded. And if it's unbounded, then clearly it cannot be a classical solution. And since the family U lambda is constituted with minimal solutions, they are ordered. And that means that for lambda equal to 0, we have the obvious solution 0. And as lambda moves towards lambda star, the family U lambda increases towards U star. And you see, since U star is unbounded, the only thing that can happen to the curve is to have a vertical asymptote in the U lambda L infinity norm lambda plane. Okay, so this is the first scenario. Second scenario is when U star is a bounded function. And in this case, what we're going to prove is that in fact, due to elliptic regularity, U star is going to be a smooth function. Okay, but then if it is smooth, it belongs to the space in which we applied the implicit function theorem in global form. Let's say it belongs to C2 alpha, for example. And that in particular implies that since the implicit function theorem stops at U star, that the principal eigenvalue of the linearized operator computed at U star has to be equal to 0. Because if it were strictly positive, then we could continue the curve beyond lambda star, contradicting the very definition of lambda star. So here we have the following picture. Again, in the y-coordinate, we have the L infinity norm of U lambda, and in the x-coordinate, we have lambda. And we have a curve of solution, which this time stops at lambda star. Okay, so once we've established this blow-up alternative, this will reduce the question to figuring out when is the extremal solution a bounded function. But first, let us prove what is missing. That is that if we have a bounded extremal solution, then in fact it is smooth. Okay, so let us assume that U star is bounded and prove that it is smooth. So the first thing we can observe is that the function U lambda for lambda strictly less than lambda star is a smooth function. And U lambda is going to be less than U star, and so this whole thing is going to be less than some constant, an L infinity of omega, sorry. Okay, so this we know. And as a consequence, the right-hand side of the elliptic equation is going to be bounded. That's easy, okay? We can say a little more. We can even say that the gradient of this quantity can also be controlled in terms of what? So let me compute the C1 norm of this. So we say the L infinity part is controlled by a constant. And then when you compute the gradient of this, you'll get a P times 1 plus U to the P minus 1 times the gradient of U. 1 plus U to the P minus 1 is still a bounded quantity. So we can say that this is bounded by the L infinity norm of U, let's say, on omega. Okay, very good. Now you remember that Laplacian of U is equal to this quantity with 0 Dirichlet data. So now we can apply Schauder estimate, and Schauder is going to tell us that U lambda in the C2 alpha norm is going to be controlled by a constant times the C alpha norm. So I say lambda star times the C alpha norm of 1 plus U lambda to the P. But you see, we already have a control on its C1 norm, which is clearly bigger than the C alpha norm. So this whole thing is going to be controlled by 1 plus the C1 norm, gradient of U lambda in L infinity of U. Okay, but now look at this C1 norm. C1 is a space that interpolates between C0 and C2 alpha. So we can say that there exists a constant C such that U lambda is controlled by, in C1 space, is controlled by the L infinity norm of itself plus epsilon times, let's say, its C2 alpha norm. For every epsilon, we can do this. We've done this many times. This is called an interpolation inequality. So we plug that into the previous equation and we get that U lambda in C2 alpha is going to be controlled by, so some constant times 1. Then we have a constant times U lambda in L infinity, but U lambda, recall from the beginning, that is a bounded function, so we have a whole constant coming out. And then we have C prime times epsilon times the C2 alpha norm. And if we take, let's say, epsilon equal to 1 over 2C prime, let's say, then this quantity can be absorbed into here. So let me just write it here. Epsilon C prime in C2 alpha. And so we get that U lambda is uniformly controlled by some constant C, which is independent of lambda. And this is true for any fixed alpha. So now, since U lambda converges monotonically to U star, we conclude that U star is C2 alpha in omega. Okay, and we can bootstrap the argument as we've done many times. In fact, U star is smooth.